So today my talk will be focused in spin dynamics in silicon crystals. Silicon crystals enriched isotope of 29. Presentation. Oops. No? Huh? Thank you. Presentation will consist of two parts. In first part, we will discuss about possibility of use silicon crystals in quantum computing. And second one will be some spin-dependent effects will be present in these crystals, our experimental results, like as magnetic isotope effect, NMR, ESR, and dislocation luminescence in these crystals. So, some type of introduction about quantum computing. You know a lot of candidates for this. It's Cooper power, some super paramagnetic, some ion traps, so on. But exist some conditions, some rules that was discovered more or less 20 years ago by De Vincenzo conditions. It's well-known conditions for realistic quantum computer. So at first, this machine can named quantum computer if you will have no less 1,000 qubits, spin bits, qubits. So second one about correlation time. About situation when you must turn off all spin in one direction, so in initialization state. Second one, error bar must be not so high. Of course, thermal fluctuation, coherence time, so on. It's so important for quantum computing. It must be possible to perform elementary logic operation between two qubits. And of course, reliable output of the final results should be possible. So all of this, more or less, all of these rules can be used in silicon crystals. Because long spin correlation time of nuclear spin in silicon-29. It's just one isotope of silicon which has a nuclear spin. Silicon has 3 isotopes and just one has nuclear spin. And correlation time in these crystals up to a few hours at room temperature. Electron spin, for example, atom of phosphor 31, long correlation time up to 1 minute. It's so high for million operation with qubits. And we used NMR technique for monitoring nuclear spin of isotope 29. And ESR technique for monitoring spin of electrons. Yes. So let me remind a little bit about silicon. Silicon this is the most useful semiconductor for electronics, for group silicon, diamond cubic crystal structure, and has 3 isotopes, as I said, and in natural abundance, it's this concentration like this. Just few percent of silicon-29 in Chokhralsky crystals grown exist. So information is saving in the subsystem of nuclear spin of silicon-29, and logic operation can be executed by means of ESR or double nuclear magnetic resonance. Yes, thank you. Of paramagnetic centers. Yes, related to the nuclear via hyperfine interaction. So some interaction between this system, it's already described. It's already well known, and some mathematical approximation, some mathematical analysis was done. So it's a system good for modeling, for applying. First, silicon quantum computing was proposed by Kahn in 1998, so a long time ago, but it was first great idea to use silicon in quantum computing. Kahn proposed used atom of phosphor as qubit. He takes two atoms of phosphor, which has nuclear spin and electron spin. So it's two separate qubits, some distance between them. And he used two gates. Used a qubit of atoms phosphor may be manipulated by applying an oscillating magnetic field. So different field, different oscillation, you can manipulate their two spins as qubit. Another proposals was done by Professor Ito in Tokyo University, Keio University. His group proposed used silicon-29 as qubit and atom of phosphor used as K for reading spin state of this qubit, because wave function of atom of phosphor can feeling the spin state of not just a neighbor atom, but over 1,000 atom around. They used gradient of magnetic field from 7 till 9 Tesla, and each atom of 29 will precision at a different frequency. It's like a guitar. You have 7 strings, yeah, and with different frequency, you can manipulate independently each atoms, each spins. Exist another proposals, exist another models how to use silicon crystals in quantum computing, but mostly of all of them ignore the surface. A surface exists everywhere in each your samples. Surface exists. Surface is like nanoreactor with different free energy, with different chemical potential, with different chemical composition. So it's surface. And our idea was to use the specific of surface, specific of silicon surface, as dangling bonds. For example, PB centers, it's well-known centers that can check by ESR technique. It's well-known defects. Another point defects in silicon, well-known too. And we try to use this opportunity and take additional defects like linear defects. It's like dislocation, maybe. So it's linear defects. Okay, and monitor this radical pair when each of them has electron spin. Like dangling bonds, it's free electron on the silicon, and this pair with triplet oxygen. So, and you will see later that this pair can be used as qubit. So, about theoretical explanation, modeling, it's already done too. These people, for example, in these articles, describe the situation when atom of oxygen goes to the silicon bonding, and it's possible to form stable chemical bonding just in the situation when you will have triplet oxygen. So it depends on spin state of these two radicals. And this theoretical prediction was, One more slide. I'm sorry. So it's another way how to use independently to give additional spin in this pair, spin of nuclear spin. If you will have spin of first electron and spin of second electron, so you have conservation law and запрет Паули. And another physical law. So it's impossible to change projection without additional energy. If you have this situation when you have three spins, you can transition between singlet and triplet state. It's more easily. Just a magnetic field from nuclear spin or external magnetic field possible to change this projection without any energy. And this effect named magnetic isotope effect that just spin of nuclear can manipulate of chemical reaction. And we confirmed this experimentally. We used silicon crystals with natural abundances when silicon of 29, concentration of silicon 29 was so low, just few percent, 4%. And we're looking for some isotope effect, kinetic of this effect with time. And we found some dependencies, oxidation of these atoms depends on nuclear spin. What we used? We used a special technique, secondary ions mass spectrometry. When you have primary ion bombarded the surface, and secondary ion will be goes to the mass analyzer, the filter, and separate by their mass. This technique can be used not just for chemical analysis, but for isotope analysis. This technique can separate isotope and their oxygen complexes. And we found that silicon 29 involved in a reaction of oxidation reaction more often than another one isotope. But, for example, 29, it's 90%, but just few times these atoms can be involved in reaction of oxygen, this oxygen. And value of these relative changes you can see on these graphs. And we find monitoring of the system not just by XPS or WIMS, SIMS, and by IFM technique too. So by eyes, you can see oxidized or not your surface due to the hyperfine interaction. So, and another question was, it's just surface, top, or inside too? How deep this effect? Again, SIMS methods, secondary ion spectrometry, and you see just isotope and their oxygen complexes on the surface and this dash line and in the depth of 10 nanometers. And you see that some differences exist. But additionally, we move deformation of these samples. So we give some linear defects in these crystals. And what we find? In reference samples at room temperature exists some profile of distribution of three isotopes. It's okay, it's normal. Because it's crystal, it was growing, so surface again, oxidation of surface, and so on. And if you deformed your samples, this profile a little bit changed. And we found that it depends on the type of deformation. So 3-point of or axis bending. You see. just deformation, without any special implantation and so on, just oxidation of silicon-29 isotope. And we confirm this hypothesis by this experiment that it's a symbiotic behavior of silicon-29 with oxygen complexes, their profile, distribution together with silicon-29. So if this center is paramagnetic, we must see there by ESR. ESR technique to monitoring this electron spin in their complexes. On the slide, you can see several spectrum in crystal with silicon crystal enriched with silicon-29, doped with boron. And you can see a lot of lines. Of course, with G factor 2, yes, it's okay. But after deformation, we found additional line that we tried to interpolate it with holes. With holes, heavy and light holes, with internal yes, thank you. So, but angular dependencies of this line was a little bit strange. We tried to find in literature some results, some data that will like be same or not, but we didn't find any convenient. And it was idea that it must be our oxygen complexes that has additional spin orbital interaction. And we simulate the spectra by some soft Winnipeg Symphonia, and you can see our results that are more or less the same with experimental results, and the value of G factor was like this. Centers. Oh, so high. Okay. So it's confirmed our results and our idea that it happens due to the oxygen complexes. Additional information we take from photoluminescence spectra. You can see that additional line and there with silicon-20 it's an And in our samples, singlet state, a transition from triplet and singlet state will be monitored, can be read as oxidation or not these atoms. Like this. Oxidation is possible from singlet states. Its realization is equivalent to read out of information stored in spin pair. Silicon-29 with oxygen. So, it's some conclusions. That magnetic isotope effect was observed in silicon crystals. You remember that oxidation, kinetic of oxidation, is completely different for 3 isotopes. Plastic deformation of silicon crystals was made, and significant broadening of 3 isotopes and their complexes was observed. Did you remember the profile of distribution? After deformation, this profile completely changed. Plastic deformation does not affect on NMR. Yes, we tried to find this effect, but unfortunately, because concentration of this defect and around rounding our atoms of silicon-29 not affected on the line width. And symbiotic behavior of ESR spectra and photoluminescence confirm our results and idea about silicon-oxygen complexes. Yep. Thank you for your attention.
I apologize for the technical problems, but it does not change my opinion that your report has been perfect. Some questions, comments?
Thank you very much for this interesting presentation. I have one question. You have shown one transparent in which you mentioned the existence of pure spin states. And of course, everybody knows if you are interested in quantum computing, you should have pure spin states. But I cannot see in your very complex system how you really realize this pure spin state. I remember the work of Michael Mehring in Stuttgart, and he was very involved to create pure spin states for quantum computing EPR. But finally, as I understood him, he did not succeed. My question is, how you can really create a pure spin state in your very, very complex system?
Thank you for the question. It's really important questions because it's the main questions of quantum computing, initialization states. Yes. We try to do this with dislocation. Dislocation, it's linear defects that go through the several atomic plates. Yeah. So, and dislocation, it's выделенный, fixed. It's fixed. It just fixed. Just one atom, one parameter of lattice on the dislocation. It's really fixed dislocation, linear defects in crystals. And if we have pure silicon crystals, 29, each of them will be focused on this dislocation. We try, yes, but you see this little bit more or less. But we try to use this phenomenon of dislocation linear defect to put each atoms of 29 linearly.
And these pure spin states are existing over a long time?
Yes.
Oh, yes.
Yes. More, yes.
Thank you.
Other questions? Maybe. I have one. Sorry, Professor Koval.
It's not exactly a question. It's I want to comment the following. I think that in the few next years, the magnetic resonance, including electron spin resonance and nuclear magnetic resonance, will play a very important role in the created new quantum systems. Now is going on a revolution in this field. And only magnetic resonance during 70 years or 74 years have a good experience in the manipulation of spin systems. And I only want to underline the importance of this field in the next future years.
I'd like to conclude, and I wanted to ask a very hard question. In near future, can I buy the quantum computer or not?
It's a good question. Ну, я поблатую. We are friends and I can solve.
Okay, thank you for report and